In this episode, I'm going to make a rotation matrix, and then if I create a wall object, I will be able to rotate it around its center point. Before I actually rotate a shape on the canvas, I want to introduce the rotation matrix, because that's what I will use to find the new positions of the rotated object. So here I have a circle around the origin with the radius r, and the vector from the origin with the magnitude of r, so that this point is at the edge of the circle. And if the angle of the vector with the x-axis is alpha, and I want to rotate the vector counterclockwise by beta, then the new vector's angle with the x-axis will be alpha plus beta. And then I can use some trigonometry. If I have this right triangle here with the hypotenuse of r and the angle of alpha, then the length of the adjacent is r times cosine alpha, and the length of the opposite is r times sine alpha. And that makes the coordinates of the vector's endpoint equal to r times cosine alpha and r times sine alpha. And I can use the same method for the point after the rotation. The new vector's endpoint coordinates will be equal to r times cosine alpha plus beta and r times sine alpha plus beta. And I can rewrite these two expressions based on the trigonometric identities for cosine and sine, so that I will get for the xy value that it's equal to r times cosine alpha times cosine beta minus r times sine alpha times sine beta. And I can replace this expression to x0 and this expression to y0, because here I can see that it's the same. And that means that I can write the new vector's x coordinate as x0 times cosine beta minus y0 times sinus beta. And using the same ideas for the y1 value, that will be equal to x0 times sine beta plus y0 times cosine beta. And now I can see the connection between the original point and the rotated one. If I write these trigonometrical expressions in a matrix form, which will be the rotation matrix, then all I have to do is to multiply the matrix by the original vector points, and I will get the new vector points. And that's what I need to do every time I rotate a vector around its starting point. I take the rotation matrix of a given angle and I multiply it by the original vector's coordinates, and the result will be the coordinates of the new vector. So I go to the code to implement the rotation matrix, but to do that, first I create a really basic matrix class right after the vector class. It will only have one method for now, and that will be multiplying the matrix by a vector. The class constructor will take two arguments, the number of the rows and the number of the columns, and the values of the matrix will be stored in the property called data, which will be used as a two-dimensional array. And as a starter, I iterate through every row and set each value to 0. And then I implement the method that takes a vector and it multiplies the matrix and the vector, and it returns with the result of that multiplication, which will be another vector. I'm going to expand this matrix class later, but right now this is enough. And I can now create the rotation matrix. I will do it here. So the values of the rotation matrix depend on the angle. So I create a function that takes an angle, then I create a matrix and fill out the values, and the function returns with that matrix. So the values in the first row are cosine and minus sine, and in the second row it's sine and cosine. And that's how the rotation matrix looks like. To demonstrate that this actually works, I'm going to use the wall class in this episode instead of creating a new class. So I put one on the canvas instead of all these. I only need one wall. Beautiful. Now I have the key control function somewhere here. And problem with this is that it was made for moving only balls originally. That's why it gives the values of these booleans, and then it also tells what to do when they are true. But this part here is useless for the walls, so I cut it and I create a ball method called key control. Then I rename the remainder of that function to user input. All this function is doing now is it's keeping the boolean value true as long as the arrow key is pressed. And now I create a key control method in the wall class as well. First, for testing purposes, I say that if the left key is pressed, then the wall will be shorter by adding a -1 0 vector to it. If the right key is pressed, then I add a 1 0 vector to it so that it will be longer. And the wall class will have a reposition method, just like the ball class does, which I will use later. And down here at the iteration through the wall class, I'm going to add these two new methods and see if it's working. It's not working because I forgot to call the user input function, which I will do here. And also key control function doesn't exist anymore. And now I can see if I push left and right, then the wall is either shorter or longer. The reason this will be useful in the future is that now I can give a key control method for every new class I'm creating later. Now I have everything ready to rotate the wall with the left and right arrow keys. I only need to modify some parts here in the wall class. Here. So first I create a center property, which will be the point halfway between the start point and the end point. I will rotate the wall around that point. I also create a length property, which will be the magnitude of the vector from the start point to the end point. And of course, there will be an angle property as well. And I create some reference points, the ref start and ref end and ref unit. These will get the values in the beginning and will remain the same all the time. Whenever I use the rotation matrix with the angle, the new direction will be calculated relative to these reference values. The start and the end properties and the wall unit will get the same values when the wall object is created, but they will be updated frame by frame and the wall will be drawn based on these constantly updated values. So the angle will be changing, which will provide new values to the rotation matrix, and that will result in a new direction vector whenever it gets multiplied by the reference unit vector. Then the new start and new end points get calculated, and I draw the straight line between those new points. One last change is that just like I didn't control the position values directly for the linear movements, but by changing the linear velocity, I will do something similar here and change the value of the so-called angular velocity. that is the change of the angle over time. I create a new property and give it a value in the key control method if the key is pressed. Then in the reposition method, I add the value of the angular velocity to the angle and multiply it by a number a bit less than 1 so that it will slow down, looking like it's getting some friction. And that's how I can apply the rotation matrix to turn a line around its central point. Instead of rotating walls, I will make a new class in the next episode, the capsule, and I'm going to combine linear and angular velocity on them.